All right, if you're jumping into calculus, there's one single idea that you absolutely have to get your head around first. It's the foundation for, well, everything that comes after. We're talking about the limit. It's kind of like the secret code that unlocks the whole subject. So, let's crack it.
So, let's start with a little puzzle. Take a look at this function. Now, if I asked you to figure out its value when x equals 2, what's the first thing you do? You just plug in the number 2, right? I mean, that's what we've always been taught. But watch what happens when we try it here.
And we get 0 divided by 0. Uh-oh. What in the world does that mean? Your brain might be screaming that the answer is 0, or maybe just undefined, move on. But in calculus, 0 over 0 is actually a signal. It's got a fancy name, indeterminate form, which is really just a way of saying, hey, the answer is hidden here, and your usual plug-it-in method is broken. We need a whole new way to think. And that new approach, it really requires a major shift in our perspective. Instead of asking what's happening exactly at a point, we're going to start asking what's happening near it. This, right here, is the absolute core idea of a limit. So what even is a limit? Well, it's the value that a function approaches as your input, your x, gets closer and closer and closer to some number. That word approaches, that's everything. Imagine you're walking towards a wall, but you can never quite touch it. The limit is basically describing where that wall is based on the path you're taking to get infinitely close to it. And this is what it looks like in math language. Lim is just short for limit. That little arrow means x approaches a, and that L over there, that's the limit, the value our function is getting cozy with. So, for our problem, we need to find L as our x gets closer and closer to 2. This really shows the big shift, doesn't it? Your entire math journey up to this point has been living in that left column. Find the exact value at a specific point. But limits move us over to the right column. We're now asking a much more interesting and way more powerful question. What value is this function trending towards?
Okay, but what does approaching really mean? You know, in math, we have to be super precise. It's not enough to just wander in the general direction. To be sure, we have to investigate the approach from two very specific directions.
Think about it like you're on a number line, walking towards your target number. You have to check out the path coming from the left, using numbers that are just a tiny bit smaller than your goal. That's the left-hand limit, and we show it with that little minus sign. Then you have to check the path from the right, using numbers just a smidge bigger. And that's the right-hand limit, with the little plus sign.
And this brings us to the golden rule. This is non-negotiable. A limit only exists if, and only if, both paths lead you to the exact same destination. If the path from the left is heading towards, say, a value of 5, and the path from the right is also heading towards 5, then great, the limit is 5. But if they're heading to different values, the limit just doesn't exist. Simple as that.
Okay, so we've got the theory down. But how does any of this help us with that annoying 0 over 0 problem from the beginning? Well, to solve these kinds of problems, we can't just think our way out of it. We need to do some algebra. We need a toolkit.
And here are a few of the key tools in that kit. We've got factorization, which you've probably seen before. There's rationalization, which is super handy when you see square roots. And then there's using some standard pre-proven limits. These are the algebraic tricks that let us peek behind that 0 over 0 curtain.
Now, for the puzzle we started with, the perfect tool for the job is factorization. It's a technique you probably learned a while back in algebra, but trust me, we're about to use it in a seriously powerful new way. All right, it is time for the big reveal. We've got the concept, we've picked out our tool, let's put it all together and finally solve this thing. Let's walk through this together. First up, we factor the top part, the x squared minus 4. That breaks down into x minus 2 times x plus 2. Now, here's the magic step. Do you see that x minus 2 on the top and on the bottom? That was the term causing our whole 0 over 0 mess. And since we're only looking near x equals 2, not at x equals 2, we can actually cancel them out. We're left with a much friendlier expression, just x plus 2. And now, finally, we can substitute in x equals 2. And there it is. The limit is 4. That was the hidden value, the destination our function was approaching all along. This shows you just how powerful this idea of limits really is.
So let's make sure this really sinks in. The function itself, it technically doesn't exist at the exact point where x equals 2. There's like a tiny invisible hole in the graph right there. But if you approach that hole from the left or from the right, you get infinitely, ridiculously closer to a y value of 4. The limit found the answer even where the function itself was broken.
Getting this idea down is your first huge step into the world of calculus, but it also sets up the next big question. We know what value the function is heading towards, but what if we want to know how fast it's changing at an exact instant? What's its instantaneous rate of change? Answering that? Well, that's the next part of the journey, and it all starts right here with the limit. Thanks for tuning in.